All right, it's 3 p.m. 01, so let's get started. Welcome to this session, and thanks everyone for joining DVCon EU. We are very happy to have you. My name is Alexander Rath from Infineon, and I am the technical program chair of the conference, so I'm responsible overall for the technical content of this day. But here in this session, my role is more the role as a session chair. So I'm moderating the session and also the Q&A in particular. And before we actually start, one reminder from my side, please join us in the virtual experience world for the closing session at 5 p.m. 30. We will do the best paper award then in the 3D world. And one more reminder, speaking about best paper and best poster, please vote. So please take your chance to vote so that we can appreciate the authors of the posters and presentations. Okay, with this said, let's jump into the content. Our first speaker will be Sanz Carretero, who is a staff verification design engineer working for Xilinx for the last 4 years on 5G mobile broadband radio products. And she has mainly focused on the areas of analog mixed signal verification and testbench architecture. Previously, she worked for Intel 5 years on a variety of products from Xeon Phi processor to low power IoT devices. Low power UPF verification and testbench architecture and methodologies. She published papers, for example, in SNAC 2017, and also patents during her time at Intel. She holds a computer engineering degree from UCM Madrid, and where she completed and graduated in 2012. Anna, we are very happy to have you. The stage is now yours, and I'm looking very much forward to your talk about testbench flexibility as a foundation for success.
Thanks very much, Alexander. Hi, everybody, and thank you very much for joining the session. Hopefully now you should be able to see my screen. Is that working fine?
Yes, we see.
Hopefully in presentation mode.
Yes, we do.
Okay, perfect. So today I'm going to present our paper, Testbench Flexibility as a Foundation for Success, a verification code and methodology to achieve a flexible testbench, increase code reuse, enable parallel verification execution, and ease of integration. This is the agenda that I have for today's presentation. So first, I'll go over the motivation of this architecture and methodology, and then I'll cover the flexible testbench architecture itself and what we did to achieve it. Next, how to facilitate vertical and horizontal reuse while reducing testbench debug, and how we maximize the reuse of the sequences at the different integration levels. And finally, the conclusion. So starting with the motivation, this is one of the products that prompted this approach. Xilinx Inc RFSoC DFE is an adaptable radio platform, and it combines soft and hard IP, providing flexibility for customers for a diverse range of emerging use cases. And flexible hardware designs require a flexible verification architecture. Project cycles have become shorter to remain competitive in the market, leaving verification with very aggressive schedules. So enabling parallel verification development, reducing integration effort, maximizing code reuse, and reducing testbench debug time have become critical to achieve first-time right silicon in a short project cycle. So this is a design under test example that we used in the paper to present this testbench architecture. And this design is composed of a number of IPs that we refer to as blocks. These blocks are grouped together to form different physical hard IPs, as we can see in the top level views. And also they can be chained together to form a final system to meet their customer needs. And this is what we refer to as system level. So we had to support at least 3 main levels of integration in our testbench. So on the unit level verification, where each type of block is verified on its own, in this case, we have 6 different test benches that we need because we have 6 different block types. In the top level verification, where we have all the top level hard IPs, we needed another 5. test benches. And finally, for the system level verification, where we could have some emerging new use cases. And it is very important to keep that in mind for the architecture. So overall, and in summary, we needed for this specific example, a minimum of 14 test benches and hence at least 14 integrations, which with the wrong architecture could end up being quite painful and have quite of an impact on the project schedule. In the actual project that we used this flexible test bench architecture, it was the number was way higher than that. So what did we do to address it? One single flexible UVM test bench that supports them all. And I'm going to cover the details over the upcoming slides, but you can see here a high-level overview of what the overall architecture looks like. Okay, so let's have a look at the flexible test bench architecture. And I'm going to start covering the makefile and compilation implementation. So we implemented different compile targets to enable selective and independent compile. And we defined the required topologies, which you can see here on the right-hand side. Where we specify how many blocks of the different types are being used for that specific topology. So for example, for the unit level for block A, we specify we only require one instance. But then for the top level view of the hard AP1, in that case, we had two different instances of block A and one of block B. And the big benefit is that new topologies can be added easily in the makefile without any significant environment rework. And now let's have a look at the testbench stop. So the testbench stop uses generates and compile time defines to instantiate the selected DUT. It also generates what we call DUT wrappers. And essentially what they do is they hold the different DUT interfaces, as we can see here, and handle the encapsulation into a virtual interface bundle that then we will pass to the top level environment. This is a small code snippet of what it looks like for the block A DUT generation. So we can see that we will generate as many as number of block A exist. And then we'll connect the top level virtual interface bundle and later to be passed through config.db to the environment. Okay, we'll cover next configuration. So starting with the prerequisites, we want to exploit the benefits of constrained random verification while still being able to provide the capability to allow for directed testing. And another key point is to have a maintainable and scalable configuration to facilitate horizontal and vertical reuse. So the implementation that we put together looks as shown in the diagram, where we have one top-level configuration object that creates and encapsulates any other block configuration object that exists in the environment. So you can see here we will have the different block-level configuration object created. And this top-level configuration object, it also allows for inter-block dependencies for system level. So we have a small example here where we can see that block A and block B both have a random variable called uplink mode. And in the case of the topology for system level, what we are making sure is that this variable is aligned between the two of them. And the most important thing is that the object hierarchy mirrors the component hierarchy, as we can see in the diagram. We also follow the same encapsulation strategy at the lower levels, as we can see with the block environments and configs, which include any other components configuration and so on. So we can see if we will generate as many block A environments as number of block A are required for the DUT. And mirroring that, we'll have the associated configuration objects here, and then any other subcomponent that exists. The associated configuration object will be also encapsulated as part of the block A config, mirroring that. So you will see how this systematic structure where we mirror the component hierarchy is also applied to other testbench places such as virtual interface bundles, virtual sequencers, but I'm going to cover that in a few slides. Okay, so we'll cover next the configuration class structure and inheritance. So starting from the left-hand side, we can see that we created a shared class called block-based config. And that is being shared for all the block configuration objects. And some of the members to highlight would be, for example, the ID in the case of multiple block instances. We also have a test configuration object that will define the test sequence that we will run, and the stimulus configuration object. Excuse me. So moving to the blocks configuration, so they extend the block-based config that we just covered, and they encapsulate any other existing component config declared as random, as well as any other variable or knob that is required for block A configuration, and that could be both verification knobs and the UT configuration knobs. No configuration variables are set up through config.db, but I'm going to cover the details on that later. So all of them would be declared as part of this block A config and as a random variable and with the associated constraints. And finally, for the top level configuration object, it extends UVM object, and it will exclusively hold any blocks configuration object and cross constraints for system level. Sorry, I think I just went on mute. Can you hear me now?
Yes, we can hear you.
Okay. In terms of the configuration randomization, we randomize the top level configuration object at the start of build phase. And because of the structure implemented, the full object hierarchy is created and randomized. So that means that all the intra and interdependencies are resolved at this point. So we end up with a coherent and valid view of the testbench topology and the components configuration, the sequencing that is going to be run by the test, the DUT configuration that we are going to apply, and the stimulus that the test will use. This methodology does not allow for configuration manual intervention from this point on. Since the constraints have been and dependencies have been already resolved, we could end up with an invalid setup if we do so. So you might be wondering if changes are not allowed from this point, but I do want to intervene at some point in that randomization process or provide some input, whether it is to constrain further or to do the opposite. How do I do it? So we use two main different techniques. We use pre-randomized and +args. And this is actually a very efficient technique. Probably you're familiar with +arg, as there is no need to recompile, and you can still rerun the same test with multiple configurations. So let's have a look at the code here on the right-hand side. So block A config in this very simple example has a member that is an integer called num, and the constraint defines that the valid range for this variable is between 1 and 16. So if we want to direct the test to, let's say, we want num to be specifically 8, we can just apply a +arg. And as part of the pre-randomize, we will take that value. And with this constraint, we will enforce num to be that value. In the case where we just want the full randomization, this else will apply, will disable the constraint. So this one here, and then we'll get the full randomization. Following this approach, tests can be reused as is for multiple use cases. And the second technique is inheritance and UVM factory overrides. So following the same block A config example, let's imagine that in this case, we want to reduce the range, but we still want a range. So we extend block A config, we create a new one for a specific use case, and then we implement our new constraint. Then as part of the test, the only thing that we need to do is just apply the factory override by type. Following this approach and architecture, tests are essentially configuration overrides. As we can see in the code, nothing else. It's fairly simple. Okay, and finally, let's have a look at the environment. So the environment creates any sub-environments to meet the DUT topologies specified by the makefile. And in the paper and throughout this presentation, we used dynamic structures just for simplicity. But since we are compiling all blocks verification collateral, there is a longer compile time. So the recommended, or what we recommend is what we call the compile time optimization, which is best, especially if the design has a high number of different block types. And you can see here what the code would actually look like with all the precompile if-defs. Okay, so following that, this is what we did to facilitate horizontal and vertical reuse and reducing Testbench debug. Excuse me. So this is what we call the object-oriented programming style integration. So what we did is we removed all the UVM config.db calls that are often used to pass handles in the testbench and also configuration variables. And the main reason is that they are string-based searches. And in the end, and because the database will keep increasing as we keep adding entries to it, it has a performance impact that becomes unacceptable. So there is only one exception. We have a single UVM config.db setGet call used as there is no other way to pass the interfaces from the testbench top to the environment, but that's the only call that we have. So for the configuration objects, we can see in the code on the right-hand side. So this is a top environment build phase. And as we covered previously, we'll create the top configuration object here and we'll randomize it. And after that, what we do is we pass down all the different handles to the different block environments, sorry. And the block environments, they will do the same, they follow the same approach to set their environment's configuration object as part of their build phase. To set the different interfaces, we retrieve the virtual interface bundle, and then we'll pass down to the blocks virtual interfaces for them to redistribute following the same approach. Similarly, with the virtual sequencers, they encapsulate any other sequencer and pass on the handles. So you can see that we follow the same systematic approach, right? And finally, for the sequences to retrieve the necessary handles, we created a method that needs to be called before the sequence runs, where it retrieves the handles from the parent sequencer. A good place where this function can be called could be pre-start or pre-body tasks, so that the sequence, when the sequence is started, it will be automatically called in the background. Okay. So on the constrained random approach, this also helps us reduce testbench debug time due to the UTM's configuration by using the fail early approach. So since we randomize it at the start of build phase, any constraint conflict will be flagged at this point. And because of the systematic architecture and methodology, we were able to automate the generation of the main testbench skeleton classes at the start of the project. So we secured a strong foundation with which to begin. These classes included all block level environment packages, the basic handle setup, the top level environments, including all blocks integration, excuse me, and the testbench top, etc. And last on this section, we have the briefly on the SVA strategy. We avoided any use of absolute hierarchical probes to be able to reuse across topology changes. And so we made use of binds and relative hierarchical probes if required to facilitate vertical and horizontal integration. And now into the last section to maximize reuse of test sequences at the different integration levels. And I'm going to start with the sequences first. So all blocks share a common parent class block-based virtual sequence for the unit level virtual sequence. And this parent class implemented a common sequence flow with different tasks that the child classes can implement to suit their needs. This helped unifying the structure and also reusing code. So we can see here an example of the sequence flow where we can execute power on reset, initialize the block, configure block, etc. And this parent sequence also provides some configurability through the test config object, which included mid-reset trigger support as an example. And if you want to know more about the reset methodology, the next presentation, WeiWei will cover what we did there. And any system level sequence would also extend the block-based virtual sequence class and will implement similarly the same parent tasks. But in this case, we would do it by reusing what we have already from the unit level. So we would call the different tasks from the unit level virtual sequences. This implementation allows for full flexibility to tailor the different tasks flow if there is any synchronization required between the blocks phases. Okay, and next I'll cover the tests and the sequence integration. So we use the top base test class, which creates the top environment and hence any other sub-environment matching the topology. And then each block would create its own block-based test. And this would be used as a parent class for any other test case. Similarly, the system level base test would do the same, would create a base test and then a specific test case or use case would extend this class, this common class. Any child class test case is kept simple, mainly implementing configuration overrides as required. And the unit level block base test would create then handle aliases to the environment. So remember that the parent class creates the full top level environment. But if we only target a specific block, so in the case that we have multiple instances of the same block, it is handy to create the aliases so that we can target a specific block ID. So what we did is we implemented a plus arg ID to specify which instance was used in the case of multiple, for example, for the top level hard IPs. And by following this approach, we were able to reuse 100% of the unit level test cases without any changes for top level verification. And for system level, it was a bit different. So we already covered the new virtual sequence implementation. And then we also needed to implement new constraints as part of the top level configuration object to ensure that the blocks that are going to be interconnected are aligned, as well as the UVM components are being set in the right mode. The system level base test would then run the system level virtual sequence and apply the configuration overrides to activate the system level constraints. And putting it all together, this is for all the different levels of integration, this is the structure that we implemented. So to conclude, we achieved a single flexible UVM test bench that supports all the integration levels that we required, de-risking potential top-level changes, providing a flexible framework for new custom system-level use cases with maintainable and reusable coding that facilitated vertical and horizontal reuse, also minimizing test bench debug time, and maximal reuse of tests at different integration levels. We achieved 100% of vertical test reuse from unit level to top level. This test bench architecture and methodology was used to successfully verify Xilinx RFSoC DFE, and the presented guidelines and techniques are generic, so they can be applied to other type of ASIC and SoC designs. And that's the end of my presentation. I hope you found it useful. Thank you very much for attending, and I'm happy to take any questions from now.
Thank you very much, Anna. Great presentation. Spot on. It's exactly 3 p.m. 25. We have more than 40 participants in the call, so I'm sure there are some questions. Please shoot.
Hi, I'm Peter Nuts from Keysight Technologies. I noticed that I forgot the name, not the blocks, but the hard IPs, I think, that they had all the blocks in parallel, which allows you to indeed run the same test that you use for a block at the higher level. Have you also used this methodology for higher level DUTs where the blocks are in series and you cannot just test one of them?
Yes, that would be similar to what we did in system level, right? That'll be closer to that.
Yes, I think so.
Yeah. So in this case, okay, let me go to the diagram quickly. Sorry. Okay. So this would be it. So in the case of the top level view, there would be a minimal amount of logic at the new level.
Yeah.
But in the case of the system level verification, we did have them chained together. So it is a bit more complex in terms of how you set up both for configuration on the different blocks, as well as the test bench being aligned and having all the components in the right mode, you know, for checkers and monitors to be in the right active passive fashion.
And so you reuse your, well, I was wondering how you reuse your unit tests in that case, but I guess if you have monitors in between, then you can.
Yeah, so the 100% reuse happened on this one.
Oh yeah, okay. Yeah, that was
on the system level, it was different. We had to implement the new constraints to make sure that the configuration was aligned between the blocks, and then also the sequence. So if I go back to the last section, the sequence is new. Sorry. Yeah. So if you can see here, this is new implementation. We reuse the unit level.
Yeah, you reuse them, but you have to write something around it. Okay.
Yeah, you still need the constraints. Yeah, and any other synchronization required if there is any dependency that you need to handle.
Okay, thanks.
Thank you.
Thank you. Are there any more questions from the panel? Seems not the case. I have one more question, Anna. You mentioned in the section OOP style integration that the string-based searches of the configuration database are a performance problem for you. Do you have by any chance some data for us that to give us a bit of a feeling what that means?
I'm afraid I don't, but there is also a very good reference on that point, which is this paper that where the authors also agree that, you know, well, the main point is, if you think about it, if you use every single variable that exists to be set through config.db and the handles, and you have many blocks, and then when you go to top level, you even have more instances, like it just explodes very quickly, and it is a string-based search. So that does have an impact. I don't have any profiling numbers, unfortunately, but this is also a good reference of Chris Spear paper.
Okay, cool. Thank you. All right. Any more questions? Seems to be not the case. Then thank you very much, Anna, for the talk and for answering the questions. I hope we see you later then in the 3D world, so that people could ask more questions if any. Also, the best paper award will be done or given in the closing ceremony at 5 p.m. 30. So we hope to see you then there in the 3D world for the ceremony. Yeah, and please everybody. Yeah.
Thanks a million.
See you then, and also a reminder for the panel: please vote for the best paper award. Yeah, and for the best poster award. Okay, then let's move on to the next talk. As the next speaker, we have WeiWei Cheong from Xilinx in Edinburgh. She's a verification engineer there, and she started working at Xilinx 3.5 years ago. And she has been intensively working on verification for several IPs, such as soft decision FEC and RF SOC digital front-end IPs. And primarily she uses UVM as the main methodology for her projects. And yeah, it's actually the first time that she's about to give a talk at DVCon EU. So we look very much forward to it. So WeiWei Cheong, the stage is yours. And I'm looking forward to your talk, handling asynchronous reset testing by building reset awareness into UVM Testbench components.
Thanks, Alex. So I hope that you can hear me clearly.
Yes.
And I'm going to share my screen. Okay. So, can you see my slide in presentation mode?
Yes, we can.
Okay, then I will start. So hello there, my name is WeiWei. I'm a verification engineer and working with Xilinx under the wired and wireless group. And I work with Anna on the one of the DSP project. And today I'm going to present the DVCon paper that I've contributed this year. It's about a reset handling and testing methodology we use in one of the DSP IP verification project in Xilinx, and this reset methodology is implemented by building reset awareness into the UVM Testbench component. Bring up the laser. Okay. So here is the content of my presentation today. I will give an overview on what normally we want to achieve in doing a reset testing on the hardware design that we verify. Then I will briefly go through some existing reset methods we can find online. And next, I will explain in details about the reset methodology we propose in the paper. And then I will end with a summary and some future enhancement we could have on this topic. Okay, first of all, what do we actually want to achieve in a reset testing? So typically a reset testing is a very common procedure we need to do to verify an IP or a piece of hardware design. And usually you need to do the reset testing to get a good coverage in both functional and code coverage. You might want to do a graceful reset, which assert the reset when the DUT is idle without any traffic, or you might need to do a reset for the DUT to kind of recover from any error handling conditions. And I think among this reset scenario, I think the most disruptive one will be doing a reset at a random point in a simulation and with some in-flight traffic ongoing, and we might want to trigger the reset multiple times throughout the simulation to verify that the DUT is able to kind of enter and exit reset phase cleanly, and its performance still compliant to its specification after the reset process. So this kind of reset testing can be very disruptive to the DUT, and it can also be very problematic to the test bench as well. There are some UVM test bench aspect we need to pay attention to when we handle the reset, and I'll talk about them in the next slide. So now let me quickly go through what a test bench needs to have for a reset testing. And the test bench need to be able to drive reset randomly, and the test bench components must be able to detect the reset event and execute the reset flow. And once the reset is lifted, the test bench is ready to start sending transaction again. So those are the test bench expectation for reset testing. And on the right-hand side, this is a very simple test bench architecture that I use for this paper. So as you can see here, I have a clock agent to drive the clock, a reset agent to generate and trigger reset events, an input agent to drive input stimulus, an output agent to receive output transaction from the DUT and send it to the scoreboard for checking. And also I have a model to generate prediction based on the input. And as you can see, all the components here, they are all subscribed to the reset monitor. So in the reset methodology we propose is a requirement that all the test bench components that needs to be reset aware to have a reset TLM port to receive the reset sequence item that has been detected and broadcasted in by the reset monitor. So this is how they know a reset has occurred, and upon detecting the reset, they will run their reset routines accordingly. And one thing to note is that all the components in this test bench is in the same reset domain. Okay. So I did mention just now that a random reset event is kind of problematic to the test bench, and I'm going to briefly explain the reason. And on the right-hand side, this is a conventional stimulus generation flow a UVM test bench would have. So normally you would have a sequence started at the test or virtual sequence level to generate a stimulus. And in the sequence itself, one or multiple sequence item can be set up, and then they will be sent to the driver via the driver sequencer communication mechanism. And the driver then converts the information carried in the sequence item into the interface level activities and drive it on the DUT. And after consuming the sequence item, the driver calls item done. And with that, it completes the driver sequencer handshake. So as a random reset event can be injected at any point of a simulation. So it's very likely that a reset happens in the middle of a driver sequencer handshake and cause interruption on the sequence execution flow. And killing a sequence abruptly potentially will result the driver trying to return a handshake to a sequence that has been removed from the sequencer, and that will actually cause the handshake in deadlock and a fatal error in the simulation. So it's very important to bear that in mind when you design a reset flow for your test bench. We kind of want to avoid the driver from returning anything to a sequence that might no longer be there due to a reset. So, and I did some research around the reset testing previously, and I found out some existing methods we have online. So I think it would be useful to just share this with you as well. So from what I found, I categorized them into two groups. So one of them is utilizing the UVM phase jumping method to do the reset testing. And here are all the built-in UVM phases, and they are launched in this order in a simulation. Theoretically, we can use the phase jump function called in the UVM to jump from any simulation point back to the reset phase and run the reset routine and then start over again. And we can do that as many times as we want. And that's the theory. And it's quite hard to find good documentation and or examples online to actually know how to use this phase jumping method. And in fact, there are some verification experts don't recommend people to use this, quoting that the UVM communities are still trying to enhance it, and there are some known issue around this method. So yeah, so the recommendation I got seems to be only use this method if you are prepared to deep dive into UVM source code to really learn how to use it. So if any of you have any good example or documentation around this UVM phase jumping, welcome to share it with me. And another more common strategy to use in tackling the reset testing will be building a test bench, which is UVM components such as drivers, monitors, and scoreboards. They are all reset aware, meaning that it must be able to first detect a reset has occurred, and then only it can react to the reset. This is also the kind of strategy we use in our approach as well. You can find some examples online. You use this strategy, but I think the implementation details are different from what we propose in the paper. And here is one example I found. Like I mentioned previously, we need to take care of the driver sequencer handshake. So here in this example, A status field is added to the sequence item or sequences, so that when a reset is detected and the status field can reflect that the sequence item is incomplete, and this status can be propagated up to the main stimulus generation loop, and it can then initiate a change in stimulus if a reset occurs. So I actually believe that which reset methodology best to be used in a test bench is highly dependent on how the DUT react to the reset. And most of the design that I work on, the DUT will just discard any incomplete or partial transaction due to a reset. And the DUT usually retain nothing in the pipeline and just start over again after exit from reset. So with a design specification like this, this method here might not be the best solution for me, because I don't see the benefit in retaining the incomplete sequence item throughout the reset. And it would be a lot cleaner if we can just kill the driver sequencer handshake and discard all the incomplete traffic and start over without all this status propagation as what we have seen in this method here. Okay. So that finally brings us to the reset methodology that we propose in this paper. So this paper focuses in explaining the implementation of the method in the following aspects. So it explains how we run both the stimulus generation flow and the reset generation flow together in one base virtual sequence. And the reset generation flow allows us to generate multiple random reset events in a simulation. And it also contains the reset handling implemented in the input and output agent to ensure that the driver sequencer channel is synchronized throughout the reset. And lastly, it also contains example codes on how we handle reset in other UVM components such as scoreboard, model, and so on. And there are actually quite some amount of example codes being provided in the paper. So I didn't put them all in the slides. So if you want to look at the code details, I would recommend to refer to the paper. So here I've put down some code snippets for the important section of the paper. I'll quickly flash through the code we have here so that you will have a rough idea on how the classes look like on their own. And then I will explain in details how these classes work together in a synchronized way with respect to the reset timing. Okay, so first of all, let's look at the base virtual sequence. So this is where we kick off the stimulus generation of the test bench as well as the reset event sequence as well. So basically, we will enter a do while loop after the power on reset. The main thing to note in this virtual sequence is inside this do while loop, it contains 2 threads running in a fork join any block. And one is the stimulus generation thread and another one is the reset generation thread. So while we exit from this fork join any block and we have a disable fork call, I'll explain later in detail what this structure will provide us. So another thing to note is that we have a test config knobs here to control the number of reset event we would like to observe in a simulation. And we have a reset count variable to track the number of reset event that has already been triggered. And then let's look at the handling in the driver. Again, we have a similar structure, although not entirely the same with the base virtual sequence. We have an always running while loop, and we have 2 threads running. One is detecting the reset, and another one is driving the sequence item received from the sequencer. The idea is that the driver will keep on driving the DUT interface until it detects a reset, and then it will come out from this fork block and call the disable fork, and then drive the interface to its reset state, and then staying here to wait until the reset to be lifted, and then only start that again after the reset is lifted. Okay. Next, we'll look at the code for a sequencer. So the sequencer detects the reset using a reset TLM port. The main thing here we need to do in a sequencer when a reset is detected is to execute the built-in stop sequencers function. So this will terminate all the sequences scheduled in the sequencer. And another thing to note is that if you have a layered agent or sequencers in your test bench, you will need to make sure that all the sequencer used in a layered agent should be able to detect reset and call it stop sequences function as well. So again, it might not be obvious to you now how all this work together, and I will cover that later. Then for any other UVM component that need to be reset aware, such as a scoreboard or a model, we can have a structure like this here. Again, it's very similar, 2 threads inside a forever loop, one to service the reset and one to run the normal operation you want for a scoreboard. And we use a reset TLM port to detect reset event. So once we complete the reset service, and disable fork will be called. Okay, so hopefully by now you have a rough idea on how the reset handling is implemented in terms of the code structure. And now I will use flowcharts here to explain the methodology so that we can see how all these pieces work together with respect to the reset timing. First, let's assume that we are out of power on reset and we are now in normal operation mode. And at the test level, we enter a do while loop, and within that loop, we have a fork join any thread, like what we have seen just now. Under it, there are mainly 2 threads running, and the reset thread and the means stimulus generation thread. The reset threads contain the reset sequence that drives a reset event at a random point in time. The main stimulus generation thread contains the sequence that drives all the input transaction. And because this is a fork join any block, so any of these threads complete will cause the program to exit from this fork block and execute the disable fork statement. So the disable fork will kill all the active processes, which means completion of either of these threads will cause another one to be killed. And another thing that I mentioned just now, but I didn't put in the diagram, is that you can use a test config object to control the number of reset you want to do in a simulation. So one of the benefits of for this test structure is that even if you don't want to do any reset, you can still use the same test space by just setting the reset number to 0, and it will just wait in the reset thread until the main thread complete. And then now we look at the sequencer. Typically, the driver sequencer connection is done in the UVM connect phase, which is before the run phase. So when we are in normal non-reset mode, once there's a sequence called .start and pass in the sequencer, basically the sequencer can start sending the sequence items to the driver. And the sequencer is by default always waiting for receiving a reset transaction, meaning if a reset occurs, the sequencer will be notified through the TLM port. And finally, let's look at the handling in driver. So it's quite similar with the test structure. We have a fork join any thread contained in a forever or while loop. And the fork join any block is followed by a disable fork statement. So the idea is the same. The main thread will always be active when we are not in reset. And once we enter reset, the join any block will complete and the disable fork will kill the main thread. Okay. So now let's assume after some delays, the reset event sequence is started. The reset drivers drive the reset low and brings the into reset. And at the test level, you can see that we are still staying inside the fault block. This is because the same reset entry sequence will also do a reset exit flow after some delays. So we will only exit this fault block after a reset exit. And on the sequencer side, once the reset is detected, stop sequences is called. So stop sequences is a built-in UVM function that kill all sequences currently operating on the sequencer. So this essentially reset the sequencer to an idle state. So if the driver is not handled properly and it requests or returns sequence item after the sequencer calls the stop sequences function, that will actually cause the lockout we mentioned just now. So let's see how this is handled in the driver. As you can see, the disable fault in the driver will be executed the moment the reset is detected. Therefore, the main thread will be killed. So the driver will not be able to request anything from or return anything to the sequencer because the main thread is killed upon we detect the reset. And one thing to note is that the fork loop won't be restarted until the reset is lifted. So that's how the synchronization between the driver and the sequencer is handled. And there's no dangling driver sequencer handshake left behind after both reset routines in sequencer and driver are executed. So at last, let's look at what happened when we exit from reset and back to normal operation mode. And at the test level, once the reset sequence completed, the disable fault will be executed. If we haven't seen the amount of transaction we want for the simulation, we'll restart the stimulus and the reset generation flow again. And then eventually the virtual sequence ends when all the reset events have happened, all the input transactions have been sent, and all the expected output transactions have been received. Then the sequencer is back to idle state, waiting for the sequence.start to happen. So if at the virtual sequence, if we call the .start again and the sequencer then is ready to communicate with driver again and start sending sequence item. And similarly, in the driver, the fault join any thread will be restarted once the reset is lifted. So the driver is ready to receive new sequence item from the sequencer and drive them on the DAT interface. And that completes a reset testing cycle. So that's the reset methodology we propose in the paper. So to summarize, the main objective here is to build a test bench that can randomly trigger one or multiple reset events in a simulation. All active threads can be terminated cleanly when a reset event is detected and no dangling driver sequencer handshake. And normal operation can be restarted after exit from reset. And one of the benefits in using this method is that we can reuse a single base virtual sequence to run tasks with or without reset. That gives us a more flexible test bench architecture. And there are some future enhancements we can add to this topic. For example, how do we handle multiple reset domains and the best practice in handling reset in register model and register agent. Hopefully we have the opportunity to work on this enhancement and share them with you in the future. And so that's the end of my presentation. Hope you find it useful and thank you for listening. If there's any question, I'm happy to answer them.
Thank you so much, WeiWei, for your first DVCon Europe presentation. Thank you very much. Was very great. I see that there is already a question on the chat from Uwe Sim. Uwe, would you like to step up and tell us? Oh, if not, maybe then I just go ahead and read it. So Uwe is asking, have you considered putting the reset handling into a base class such as a reset aware component? An end user would then just need to implement the resettable main part and or the optional reset implementation part.
I'm not quite sure I get the idea. I'm sure, sorry for that. Maybe if you can clarify more. But this virtual sequence is actually in a base virtual sequence, and then it will kind of extended for all the, because this reset methodology is kind of reused across multiple IP, and how those IP reuse this reset methodology, they actually extend the base virtual sequence that this this reset part is in the base virtual sequence. So we kind of already put this in a base class, and it kind of extended for the IP. I'm not sure whether I understand. I answer your question.
Uwe, in case you still hear us.
Yeah, I'm listening.
Okay, perfect.
Yeah, and the question was more if, I mean, you always implement in the components, you implement that fork and join and disable whatever. This is kind of a big obstacle for end users. So the question was, everyone implementing a driver, everyone implementing a component would need to implement that fork join thingy, right?
Yeah.
And the question is, if you wrap that code into a base class, then you leave to the end user simply to implement two functions. One function, one task. One function is the reset stuff. So what happens on a reset? And the other thing is, what is your task which can be resetted, which can be terminated. That was more or less the question.
Okay, so do you mean that because we kind of dictate that the driver need to implement like a two-thread, so seems so
yeah, you mandate to implement.
Yeah, we meant, yeah.
But if you have a base class, there's no discussion. You just give the structure and the user just fills it in, and the rest falls into place.
Yeah, I think that would kind of give the whoever implement the drivers some flexibility to do that. So I kind of agree that if we have something on the base class, so that we can turn off the reset if the driver is not implemented in a way that is compatible with the reset methodology we have, and we can kind of turn off the reset methodology at the base class or override it, then yeah, I think that would be useful.
Okay, thank you. I think we have time for one more question. Is there one more question from the auditorium? Seems to be not the case. Then I just use the opportunity to also say thank you to Ezra Al-Turki from Conference Catalysts for being the technical host of this session and handling all the, with giving the presentation rights. And so just she's making sure that everything works well in this session, technically works well. So thank you very much, Ezra. And I use the opportunity to remind everyone, please vote for the best paper. Please vote for the best posters. You can have a look at them in the virtual experience. And also I remind you that at 5 p.m. 30 we have the closing ceremony with best paper award ceremony also in the virtual experience rooms. Okay, then let's move on to the next talk. I'm very happy to welcome my colleagues, Salman, Tanvir, and Markus, Brosch. So Salman is a senior staff verification engineer in Infineon, and he's working there since 2015. His responsibilities include IP and SoC verification, actually using both simulation as well as formal methods. Prior to that, he was also involved in digital RTL design, also including backend activities. Salman holds a master's degree in electrical engineering from the Technical University of Darmstadt. And I'm very much looking forward to his talk with the epic title, One Test Bench to Rule Them All. Salman, please go ahead.
Thanks, Alex. So I think we miss Markus's bio, but Markus, would you like to introduce yourself and then kick the presentation off?
Yes, I can do this. Can you hear me clearly?
Yes.
Okay, my name is Markus Brosch and I'm a senior staff verification engineer at Infineon. I started there in 2008, and since 2014, I'm focusing on IP and subsystem verification using System Verilog, but also heavily Specman. Okay, let's get started. Today, we would like to present our paper with the title, One Test Bench to Rule Them All. Our agenda contains the following points. We will begin by expressing our motivation behind this work, which focuses on efficient test bench development and bottom-up reuse. Afterwards, our proposal for an efficient test bench architecture and the advantages it offers will be presented. This will be followed by a list of requirements that we consider vital for such a test bench architecture to fulfill. The detailed architectural aspects of the proposal are then explained. Finally, we will summarize our results and give you the chance to ask questions in the Q&A. We can all agree that with continuously increasing design complexity, verification effort is blowing up. Test bench development is a significant part of this effort. Before verification can start, much time is spent on the initial setup of the test bench, and this has to be repeated with every new design under verification. The key components required, for example, sideband, clocks, and interface UVCs, need to be developed and integrated. Additionally, writing stimulus consumes significant effort, and if not implemented in a reusable way, needs to be reworked at every integration layer. Without a common test bench framework or templates, the style and quality of test benches could vary drastically and is highly dependent on the developer. Considering all the aforementioned issues, how can we be more efficient?
So the first part of our proposal is to build all test benches from a common base layer with pre-integrated key verification components. These components consist of reusable VIP for handling sideband signals, clocks, and optionally any desired standard interfaces. Test bench environments that inherit from this common base layer should easily be hierarchically reused in a bottom-up flow. This hierarchical reuse should also support stimulus reuse. We propose to automate the integration of pre-generated IP register models into test benches and also be able to reuse them in a subsystem or a SOC context. All the above mentioned features should be supported via code generation. So where do we see the advantages of our proposed features? The foremost advantage is, of course, increased reuse. This is because entire test bench environments can be reutilized without any copy pasting. This includes the ability to port test benches vertically in the same project, but also horizontally to others. Another advantage is that test benches are developed in a common and unified way. This gives a consistent look and feel for all projects, which enhances maintainability and also promotes ease of debug. By using a common test bench architecture, we also think that a high code quality can be achieved. Finally, this enables verification to start earlier and results in a shorter turnaround time. So based on our proposal, we defined the following requirements. This is more or less a recap of the proposal slide, but just to get it in. So basically, all test benches should be derived from a reusable base test bench, which already integrates the desired common infrastructure. And this hierarchical reuse should be supported, which would also enable test bench environments to be integrated together in a bottom-up flow. The vertical reuse should also not only include passive aspects, for example, checks and behavioral modeling, but also active stimulus. Register models should be automatically integrated into IP in every integration layer. The integration of multiple instances of test bench environments, including the register model, should also be supported. Finally, a code generator should support the generation of the basic test bench skeleton, inheriting from the common base environment, and also automate all hierarchical reuse requirements we just mentioned. Now Markus will describe the architectural aspects of our proposal.
We will first explain the base HDL classes and HDL module. The abbreviations HDL and HDL refer to hardware verification language for the class-based part and hardware description language for the module part. The extension mechanism used to build testbench environments on top of the HDL and HDL base layer and the hierarchical reuse concept is then explained. This is followed by an explanation of how the register model integration is implemented. We then explain how sequences or stimulus can be reused vertically. Finally, we will explain which aspects of the proposed architecture are automated via code generation. To fulfill the first requirement of having a base test bench encapsulating the common infrastructure, an extension mechanism is required in order to reuse or build on top of this. For the HDL class-based part, the class inheritance mechanism of the object-oriented programming paradigm is used. The base classes are described individually in this table. The environment integrates the desired components which need to be shared amongst all test benches. All configurations for the common infrastructure as well as general control knobs are encapsulated in the base configuration. The base test builds the common infrastructure environment. A base sequence class contains the base configuration handle and any desired reusable knobs and methods. Finally, the base virtual sequencer encapsulates handles to the physical common infrastructure sequencers and also implements an API which enables vertical stimulus reuse. Derived test benches are extending from the base layer classes except for the environment. This exception will be explained shortly. The HDL part of the base test bench is encapsulated in a single top-level system Verilog module, which encapsulates all desired BFMs and interfaces for the common infrastructure. Similar to the HDL part, an extension mechanism is needed to build test benches on top of the base layer. As there's no way to extend modules in system Verilog similar to classes, another method is required. We consider the system Verilog binding and hierarchical upward referencing features as a good solution to this problem. With this approach, a derived test bench can simply be bound into the common HDL base module and directly reference its interfaces, BFMs, and parameters. To be able to configure the common infrastructure and to control general aspects of the test bench, the base HDL layer provides various configuration knobs. The common infrastructure for our test bench consists of a clock, sideband, AHB, and SPI UVC, and hence we have dedicated configuration objects for them. When test benches are reused on a higher level, they need to be switched from an active to a passive context, as the interfaces of the reuse test bench will be driven by the higher level environment. All drivers in the reuse environment need to be disabled. This is achieved with the isActive configuration knob. Coverage and concurrent assertions can be controlled via HasCav and HasSVA. As some test benches may not contain all supported standard interfaces, knobs are provided to be able to configure them. Additionally, building of the register model is also configurable. A global checks enable knob is provided to disable checks if required. An additional knob allows selective enabling of checks that are only considered in an IP and not in a system context. This was done as we anticipated potential performance degradation on top level. Now Salman will explain how we are inheriting from the base layer and enabling hierarchical reuse.
Thanks, Markus. So SOCs are typically broken down into IPs and subsystems to manage complexity. These blocks can be developed by various teams working in parallel and integrated in a bottom-up flow. Verification at each integration layer may or may not reuse lower-level test bench components or environments. In our experience, reuse of components rather than environments is more common. This is a more straightforward approach can easily lead to scaling issues, either when the components have to be reused or when required to be repeated for higher integration layers again and again. Additionally, the details regarding interconnection of components has to be taken care of. So complete environment reuse solves the aforementioned problems, but it also introduces its own sets of challenges. Primarily, the test bench architecture and setup becomes more complicated, as test benches at various integration levels have to coexist in a single environment. Also, as we have a single common infrastructure, it has to be shared amongst all test benches. However, the advantages of reusing complete environments outweighs the challenges. This is because all passive aspects, including checks, coverage, and transaction modeling can be reused. For complex environments that, for example, encapsulate bus systems, the interconnect setup can also be inherited rather than redoing. This can be seen in this example where the bus infrastructure at each layer is extended. So subsystem 0 contains the bus master, and when developing subsystem 1 on the next layer, we do not have to repeat this modeling again. The same goes when moving to subsystem 2 and so on. In some cases, stimulus can also be vertically reused. This was particularly beneficial in our project and will be explained in the following slide. So in UVM, the test is the topmost component in Testbench and is responsible for building and configuring the Testbench environment. Typically, all tests in a Testbench are extending from a base test. And in the proposed architecture, the base test of each Testbench is deriving from the common infrastructure base test class. This way, every Testbench can build its own environment on top of the common infrastructure. The environment configuration of each Testbench is also inheriting from the common Testbench configuration object. This allows the extension of Testbench-specific knobs and also to configure the common infrastructure environment. As seen in the figure, the environment is the odd one out, as it's not extending from the common infrastructure environment. The reason for this will be clear in the next slide. Okay, so this figure illustrates the configuration and building up of an IP Testbench and the common infrastructure environments. The IP Testbench base test extends from the common layer base test. The code depicts the build phase methods of both tests. In the build phase method of the IP Testbench, the createTB configuration method creates the configuration object and sets the knobs as desired. As mentioned in the last slide, a single configuration object is used to configure the derived Testbench as well as the common infrastructure environment. Then the IP Testbench itself is created. The configuration object is then passed to the extended IP and the common base environments. After this, the super.build phase call will then build the common infrastructure environment, which is visible in the lower half of the code snippet. Here, the common Testbench environment is built using the configuration object that was passed from the IP Testbench. As just mentioned, every Testbench builds its own environment on top of the common infrastructure. This figure illustrates how this is all working. At the top, you can see the common base layer, which every Testbench is extending from. Here in the middle is an example of an extended IP Testbench. What we would like to highlight here is the decoupling of the Testbench and the common base environments. As can be seen, the IP Testbench environment does not extend from the common base environment. Instead, the common base environment is inherited via the base test extension. This was explained on the last slide, which was the calling of the super build phase that resulted in the building of this common base layer environment. Both environments are configured with a single configuration environment, which is extended from the base layer. This derived Testbench environment, or any Testbench environment for that matter, can be directly plugged into a higher integration layer. And this is exemplified in the lower bottom of this figure. And here we see 4 IP Testbenches being reused in a SOC context. And the reuse environments can be reconfigured as desired. If we consider this SOC as a subsystem, this in turn could also be reused in the next layer of integration. So in the previous slide, we discussed how the HDL side is working in terms of the common infrastructure. Now let's look at how the HDL base layer is structured and the mechanism we're using to extend this. As illustrated, the HDL part of the common Testbench is encapsulated in a single top-level system Verilog module, which in our case includes BFMs for HB and SPI. As the sideband and clocks BFMs are highly Testbench specific, these are instantiated in IP or subsystem Testbenches as shown below. In order for the derived Testbenches to connect with the common infrastructure, they're bound into the top common module. Hierarchical upward referencing enables all common components to be resolved. On the left-hand side, you can see an example for an IP Testbench where all the required BFMs and the DOT are instantiated. This Testbench can be plugged into higher layers of integration, as shown on the right side. For vertical hierarchical reuse, the Testbench modules require a parameter to allow switching between IP or SOC contexts. The active components and the DOT are only instantiated in an IP context. As you can see on the left side, the IP context parameter for IP ATB is 1, which results in the instantiation of IPA. In the SOC TB on the right, the instantiation of IPA and IP ATB is switched off, as it's already part of the SOC DOT. Additional parameters can be added as required. An example in our Testbench are the HB index parameters that are used to connect HB slave agents to the desired HB HVL environment in a reconfigurable way. Now Markus will explain the register model integration concept.
UVM register models are usually generated from a register file specification, for example, IPXACT, and this is typically done on an IP basis. The generated model needs to be integrated into the Testbench, which requires various steps. A bus adapter needs to be defined. Additionally, the bus sequencer has to be connected and the bus-specific front-door extensions need to be implemented. Finally, bus monitors are connected to the predictor. When moving to a higher integration layer, not only do these steps have to be repeated, but additionally, all register blocks first need to be combined into a system context. Now the question is, how can all these aspects be efficiently handled with automation? Our goal was to be able to automate the integration of pre-generated IP register models and also reuse them in the subsystem or SOC context. As illustrated, the register model blocks are encapsulated and built in the respective testbench environments. On the left-hand side, you can see an IP testbench that integrates a single register model block. When this testbench is integrated on the next layer of integration, as depicted on the right side, the encapsulated register model block is reused. The SOC and subsystem level register model encapsulates handles to the lower level blocks. The lower level testbench environments maintain the responsibility of building their register models. All the integration steps, for example, predictor, front door, and adapter setup, need to be done for each testbench environment. However, these parts are switched off or reconfigured when the testbench gets reused on a higher level. Here you can see simplified code snippets of an IP testbench environment with focus on the building of the register model. The register model predictor and adapter are created, and the model is built in the build phase of the environment. At the end of the build phase, the model is locked and the front door for every register is connected. The code for a subsystem or SOC environment is the same as for an IP, with the exception that the register model is not locked and the front door is not set up in the build phase. This is because the lower level register models are not built yet. The building of the complete register model hierarchy will proceed top-down. The integration of all register blocks into the top register model will be done in the connect phase, which is bottom-up. Finally, in the connect phase of the base test, the model can be locked and the front door connected.
So after building the register model, it needs to be set up. So as Markus explained, the configuration of the bus sequencer, monitors, and adapter all has to be done. For subsystem and SOC environments, additionally, the integration of all lower level test benches also has to be done. So all these aspects are handled inside a dedicated function, which is here named connect-reg model, and is defined in each environment. This accepts two arguments, namely handles to the bus monitors and the predictor. As is visible in the bottom code snippet, this function is called in the connect phase of the testbench base test. The reason for the null predictor argument in this call will be explained in the next slide. This example shows a SOC or system level testbench environment that's encapsulating two IPs. For such environments, the top connect reg model function is calling all lower level functions recursively. For IP testbenches, this isn't required as no lower level testbenches are integrated. Now we would like to explain the connect reg model function inside an IP testbench environment. As explained in the previous slide, the function is called in two ways, namely in a standalone or an integrated context. The predictor argument is used to distinguish between these two contexts. As previously mentioned, the base test is always calling this function with a null predictor argument. This is because the top environment is always building the predictor. Hence, as visible in the code block, detecting a null predictor argument means that we're in the top or the standalone environment for an IP. In this case, all the setup steps have to be done, for example, connecting the bus monitors and configuring the predictor and so on. On the other hand, if the IP was integrated in a system or an SOC, the higher layer would have passed the top predictor handle down. Now we simply update the local predictor handle. Finally, the bus sequencer is only connected with the register model when the test bench is in an active context. For the subsystem or SOC context, the connect reg model function begins with the same code as the IP. Additionally, a few steps are required to integrate lower level register model handles into the top register model block. The first step is to set the lower level handles to the top block as shown here. As previously mentioned, the function is called in the connect phase of the base test, as at this point, all lower level register models have already been built. The next step would be to configure the top block as a parent of all lower level register model blocks. And this is done by calling the uvmreg block configure method. Now the maps of lower level blocks are added to the submap as a submap of the top block. And this is done with the configurable offset so that this can be reused in another environment. So after this, all lower level connect reg models functions are called. And then finally, the locking of the top block is done and the front door is set.
Initially, our primary focus was on reusing test benches passively. During development, we identified some advantageous stimulus reuse scenarios. that could also be supported with some enhancements. These scenarios are illustrated here. A significant number of sequences in our environment are consisting of transactions on standardized interfaces, for example, AHB, SPI, and JTAG. AHB stimulus can be remapped on a higher level to a different agent by providing a configurable base address offset. As the register model front door is also integrated with AHB, this means that register model-based stimulus can also be reused. Similarly, sequences developed in block-level test benches for the SPI and JTAG protocol can be remapped to the higher level, as these interfaces are connected directly to the lower-level blocks. We are also able to support a limited case of remapping sideband stimulus on block-level pins that are connected directly to the higher-level entity. This is, of course, not possible for pins that are already driven by the design under verification. The first step to support vertical reuse is to be able to run sequences on different virtual sequencers. As described earlier, all virtual sequencers are derived from the common-base virtual sequencer. The base sequence of every test bench uses the UVM declare pSequencer utility macro with a type parameter to specify the pSequencer for the sequence. The default value for this parameter is the type of the virtual sequencer of the providing test bench. If lower-level sequences are called from the higher level, it must be ensured that the required physical sequencers are encapsulated in the top virtual sequencer. In our case, the common infrastructure sequencers are always inherited from the base virtual sequencer. Any additional sequencers required can be integrated in the top virtual sequencer.
So typically, sequences encapsulate handles, the register model, and configuration object, which can be used to steer stimulus. As sequences are objects, these handles need to be set dynamically during the runtime before the sequence starts. Typically, these handles are pulled from the virtual sequencer in the pre-start method of the sequence. This is illustrated in the top part of the figure, where a sequence is running on the native virtual sequencer of an IP test bench environment. However, when this sequence is started on a different virtual sequencer shown in the bottom of the figure, the handles cannot directly be resolved as they are of a different type. Our solution was to basically overcome this problem by implementing a flexible lookup mechanism for resolving the handles. The lookup mechanism is implemented in the base virtual sequencer with the help of a string-based associative array and a simple set-get API. The set API is called in the base test to register all handles needed by the native and the vertically reused sequences. The get API will be called for lookup in the pre-start method of the running sequence. This is visible in the code snippet where the configuration and the register model handles for a test bench registered as IPA is being resolved.
Test benches must be built in a certain way to extend from the common base layer and support all the features that we have listed in our requirements. The first important aspect is our proposed mechanism to reuse the common infrastructure via base test inheritance. Additionally, the hierarchical bottom-up reuse of test benches, integration of register models, and support for stimulus reuse must be set up. All these aspects are automated via a generator, which has various configurations. The generator supports the building of IP test benches, as well as integrating pre-generated IP or system test benches into a system context. This also includes automated register model integration from IP to SOC. The generator is additionally automating the integration and configuration of the HVL and HDL parts of the common infrastructure, for example, clocks, interface UBCs, and sideband signals. This includes the instantiation of all desired BFMs, but also provides a template for configuration in the base test. Vertical stimulus reuse is enabled by generating the lookup code in the base sequence pre-start method, and also registering all required handles in the base tester. This test bench architecture was developed in a multi-site pilot project for the verification of a CMOS radar SoC. It resulted in the development of over 50 IP test benches that were integrated into 5 subsystems and finally into one SoC.
The subsystem and encapsulated IPs in the pilot project were developed over multiple sites. Based on our experience and feedback received from all teams, the architecture vastly reduced the verification effort. Vertical reuse was achieved without modifying or copy-pasting any existing code. By relying on a common infrastructure and having the automated capability to integrate test bench environments from IP to subsystem and to SOC, including the register model, test bench bring up was significantly accelerated. Stimulus reuse was particularly helpful as entire subsystems and IPs could be configured and stimulated with existing sequences. Without such a mechanism, the top-level teams need to put significant repetitive effort to understand how to configure a subsystem or an IP. The same applies to checks and insertions. Minimal checks need to be added on SOC level as all lower-level checks are reused. The same look and feel in test benches not only reduces debug effort, but also makes it easier to understand other test benches. Although over 50 test benches were integrated, no significant performance impact was observed or measured. Initial profiling did identify components with very high memory and CPU usage, but this was not due to the amount of test benches, but rather not following best practice coding guidelines, for example, low verbosity messaging and avoiding unnecessary transactional communication between the HVL and the HCL parts. Overall, the proposed architecture greatly accelerated verification progress on such a complex SOC. Compared to previous projects, the verification effort reduction is estimated to be at least 30%. We'd like to thank you for your attention, and if there are any questions, we'd be glad to answer them.
Thank you very much, Salman and Markus. Very great presentation. Thank you. Are there any questions from the panel? I think so, with over 40 people being present. Come on, guys. For sure, there is a question. Oh, now something. Ah, okay, here are my buttons. Okay, then I have one question. You enabled a vertical stimulus reuse mechanism between IP and SoC level. Have you thought about maybe extending this further, for example, using Perspex or something?
Yeah, that was the actual goal in the beginning. So as Markus mentioned, we wanted to first focus on passive reuse, and it turned out that with some enhancement, we could directly reuse sequences, but the end game is to actually use Perspex. So yeah, full sequence reuse would be the possible. But
so,
this is,
yeah. You are looking into that for the future?
Exactly. So this was just something that we wanted to add on, and we ran into some hiccups, and just thought that it would be interesting to just show that if your particular test benches could support some stimulus remapping, then you basically need to take these steps, basically have sequences runnable on different virtual sequences, and of course resolve any handles and stuff like that. Yeah, the end game would be to use PSS. Yeah.
Okay, cool. Since, I mean, your test bench approach covers a lot, right? It covers IP, it covers SoC. Do you have something also to, I mean, have you considered also to somehow engage this with formal verification? I mean, do you use formal verification also in this verification project?
Yeah, so basically any IPs that are verified formally, so we kind of black box that the simulation-based test bench for that IP, because that's fully verified in formal. And for the simulation environment, we still need to have that encapsulation for example, the register model for that block and stuff like that. But any detailed checking is not done there. So yeah, this is something that would be interesting for me to also figure out, that if we are doing, if you're like, delegating some IPs over to formal, then how do we, how can we still leverage, the verification done there in a simulation context also? But, yeah.
Okay, thank you. There's now also a question from Joachim Geishauser on the chat. He's asking, did you have to cover UVM_mem as well? So are you also using the UVM memory model?
No, we are basically just supporting the register abstraction. So we're focusing on the UVM reg base class. Basically, didn't come across any use case there yet with the memory.
Okay, thank you. And yeah, we are only a few seconds prior to 4 p.m. 30. So then let's stop here. Thank you very much, Salman and Markus, for presenting here. So very nice to have you. It's almost now a bit of a tradition. Yeah? I think you are here now the third time in a row or so, if I recall correctly.
Yeah.
reminder to everyone, please vote for the best paper and best poster. You see the link in the chat. Ezra has put it there. Thank you very much. And I look very much forward to meet you in the virtual experience world, where we have at 5 p.m. 30 the closing session with the best paper and poster award ceremony. And yeah, with that, thank you very much for joining the session. Next agenda point is then the keynote from Andreas Rixinger. Okay, then I close the session and wish you a nice day and a nice remaining conference. And thank you very much for joining. Cheers, goodbye.
Thank you.